So we've been talking about antiderivatives. So the one thing I really want to stress, and we'll get into this a little bit more when we'll most likely get to 5.3 today, is that remember that technically when we started in 5.1, 5.2, we were doing our Riemann sums, and remembering that that was estimating area underneath of a function. But then remember we defined that essentially the limit of those Riemann sums, if we could somehow calculate a Riemann sum with infinitely many rectangles, we would have what we defined to be the integral. So remember that those two things are related, the integral and area underneath of a function. And I say related very specifically because we'll need to be careful. We'll see in a little bit that there's a slight nuance between the two, but they are related, and I wanted to remind us of that. So here were our antiderivative rules that we found last time. So we talked about finding kind of generic antiderivatives. So we weren't finding numbers here, so these wouldn't give us areas because they're not numbers. But they're essentially how we'll be able to find these areas. Excuse me. And then we found that we can also essentially, so in the most general ones, we have the plus C, and then we can also find the C if we're given more information. And there was one last one of those types of questions that we didn't finish. So let's do that one. So this one is going to have a little bit of fractions in it, but don't panic. It's okay. So we need to find the general antiderivative first. So remember that that 3 on the outside can essentially stick along for the ride. And then we technically have x to the first. So when we use our anti-power rule, we'll get x squared divided by 2 because we add 1 to the power and divide by the new power. And then for the second piece, that 2 is going to come along for the ride, and we're going to add 1 to the power to get x cubed and divide by the new power plus c. So I'm going to clean that up a tiny bit and write 3/2 x squared plus 2/3 x cubed plus c. And remember, now that we essentially have this extra piece of information, we can essentially use that to find the c value. So we'll use f of 1 equals 3. So we'll plug in 1 everywhere we see an x, and we'll set that equal to 3. Now let's do this a little bit by hand. I know, of course, you could punch some of this into your calculator, but let's try to do the fractions by hand here. We'll get 3/2 plus 2/3 equals 3. So if I have to combine these two together, I'll need a common denominator. Maybe you're a little rusty on that, but we'll have a common denominator of 6. So to change from 3/2 to 6, I have to multiply the top and bottom by 3. So I'll get 9/6. And then to change 2/3 into something over 6, I have to multiply by 2. So we'll get 4/6 plus c. And since we're going to be over 6, let's go ahead and change that over 6 as well, and that'll be 18. So we'll get 13/6 plus c equals 18/6. Oops. And then solving for c, we just subtract the 13/6 from both sides. We'll get 5/6. So the actual antiderivative we're looking for will be 3/2 x squared plus 2/3 x cubed plus 5/6. Which is another reason I decided to stick with fractions, because the first two terms have fractions in them, so I thought it would look a bit nicer to keep that last term in terms of a fraction instead of finding it as a decimal, which would usually happen if you used your calculator. You can, of course, use your calculator to change it back into a fraction, but most people don't think to do that, which is okay. I'm not saying it'd be wrong if you put a decimal in the back. That'd be perfectly fine. But questions, concerns about that before we move on to something slightly different? Just the slightest. Wait a couple seconds in case someone's typing something. Okay. That's essentially the last question we had from 6.2, and now we have to talk about 6.3. So the fundamental theorem of calculus is essentially going to tell us how to calculate definite integrals. So the fundamental theorem of calculus was technically at the very beginning of this set of notes, but let me remind us what that said, because that was from, last week and we might have forgotten. But that essentially said that if we have the integral and if we have bounds on the integral, also know that definite integrals are the ones with bounds. So what we were just looking at, the ones without bounds, are called indefinite integrals, and definite integrals are the ones with bounds. But the fundamental theorem of calculus says that this is equal to f of b minus f of a, where notice that the integrand was an f prime. So essentially, this is going to be the way that we're going to actually be able to calculate these by hand. Now, I know that I taught you how to put that into your calculator, these ones with bounds, but we're going to want to also know how to do them by hand. Also, specifically for your homework in 6.3. So for 6.3 homework, Wiley is going to have instructions that say something like, find the exact answer. I don't know exactly the phrasing they use, but I know that it has the word exact in there. So it's going to say find the exact answer, or exact, calculate something with exact in it. And so if you were to punch it into your calculator and it gave you a decimal and you plugged in the decimal, it would tell you you're wrong. Because say it was a fraction of 14/5, it would want 14/5 instead of whatever decimal that is. And we're even going to come out to one, we'll see one in a couple seconds, where it comes out to something like, I don't know, 2e to the 5th minus 1. And your calculator will not give it to you as 2e to the 5th minus 1. So we do need to know how to do these by hand. So here's essentially how it works. It kind of starts very similar to the ones we were doing, kind of the one we just did, but without solving for c. And the ones we were doing on Friday, where the first thing we need is to find the general antiderivative. And then essentially that theorem of calculus tells us that we then plug in the bounds. So here's how this is going to work. So say I want to take the integral from 1 to 3 of 2x dx. The first thing I need is the antiderivative of 2x. So that 2 essentially comes along for the ride. Add 1 to the power, divide by the new power. So we'll reduce that to x squared plus c. And now since there are bounds here, the notation kind of changes, where we kind of remind ourselves that there's bounds to still work with. So this kind of bracket at the end is pretty normal notation. Some people will just use a straight line. I prefer the bracket notation, but whatever floats your boat. But essentially just something to note that we're not quite done yet, and we have to take care of these bounds. So at the fundamental theorem of calculus, which I'm now going to abbreviate FTC, so the FTC essentially tells us that once we have this antiderivative, we plug in the top bound, and then we subtract what we get when we plug in the bottom bound. So what we're going to do is we're going to take this bound of 3, and we're going to plug it in. And then we're going to subtract what we get when we plug in that bottom bound of 1. Every time we do one of these calculations, since we would have to distribute this negative, the c's are going to cancel each other out. So we're essentially going to have plus c at the front, and then at the back we're going to have minus c. So they're always going to cancel each other out. So we're essentially going to get 9 minus 1, which is 8, which if you punch that integral into your calculator is exactly what you get. So our integral here is equal to 8. Questions, concerns about that before we do a couple more? Okay. As always, stop me if you need to. If I'm going too fast or you want to go back to a different problem, just let me know. So we go down to the next one, the integral from 0 to 2 of 6x squared dx. The first thing we need is the general antiderivative. So we need the antiderivative of 6x squared. So the 6 will come along for the ride, add 1 to the power, divide by the new power, plus c. So we'll reduce that to 2x cubed plus c. So here, remember, in general, for the antiderivatives, I told you that I don't care if you simplify. Just like eventually it ended up being a bit better to simplify with derivatives, same thing here. Now here, it's not simplifying a ton, it's just simplifying mainly constants. But simplifying the tiniest bit can usually make your life a little bit easier for these. So once we have the antiderivative, we're going to take our top bound, plug it in. So 2 times 2 cubed plus c, and subtract what we get when we plug in our bottom bound. Now, I always suggest, I know I've been writing them, but maybe it hasn't been clear. I always suggest putting the kind of bottom bound piece in brackets, well, parentheses, brackets, whatever floats your boat, to remind yourself that if there's more than one term in there, that you're going to have to distribute the negative. Now, technically, there's always more than one term because there's the plus c, but we'll see one in a minute where there's more terms than just the thing and the plus c, and we need to make sure to distribute the negative or else we'll be wrong. So the c's cancel each other out, and we end up with 16, so 2 to the 4th is 16, minus 0. So our answer here is 16. So essentially the integrals that don't have bounds give you a function, and the ones that do have bounds give you a number. Questions, concerns? Okay. I'm going to sit in awkward silence for about 2 or 3 minutes while you guys try these two then. Try 3 and 4. I'll give you like 2 minutes before I start talking about them. All right, let's start talking about them. So the first one, your antiderivative should be 1/4 t to the 4th plus c. Add 1 to the power, divide by the new power. Plug in the top bound. Subtract what you get when you plug in the bottom bound. Whoops. You'll get, so that's going to be 0. The c's are going to cancel each other out. So you essentially just get that 1/4, 2 to the 4th. 2 to the 4th is 16, divided by 4 is 4. And then the other one, add 1 to the power, divide by the new power. The 8 came along for the ride. 5x. So 4x squared plus 5x plus c. So plug in the top bound. Subtract what you get when you plug in the bottom bound. And here's where it's kind of important to distribute that negative. So 4 squared is, 2 squared is 4 times 4 is 16. Plus 10 minus 4 minus 5. So essentially 26 minus 9, 17. Questions, concerns about either of those two? Okay. Okay. I'll hold on like 5 more seconds before I scroll up. In case people are still writing something down. All right. So these last 3 are a bit more kind of what I was talking about with the homework. Their answers are going to be a bit more not just a nice number. Well, 6 is going to turn out to be nice, but I'll talk about that a bit more in a second. So this is kind of what I mean with Wiley is that you need to be a little careful. So for this first one, number 5, the first thing we need to do is we should actually rewrite this as negative 4x to the negative third, because without rewriting it, I don't actually know how to take the antiderivative, because it's not negative 4 over x, because if it was x to the first, we would be in a natural log situation. But since it's x to the third in the denominator, we don't have an anti-quotient of anything else to deal with that. So we need to essentially force it into essentially an anti-power rule situation, if you will. So I need to rewrite it first. Also remember we have that thing with roots and what am I doing? And powers. That does come up in your homework. That's due tonight. So remember that. We still need to kind of use those 2 exponent rules every now and again. But anyway, so once we rewrite it like that, it turns into essentially an anti-power rule, if you will. So the negative 4 comes along for the ride. We add 1 to the power, so we'll get negative 2 divided by the new power plus c. So if we reduce those constants a little bit, we'll get 2x to the negative second plus c, and we need to go from negative 4 to negative 1. So plug in top bound, subtract what we get when we plug in the bottom bound. To help finish this without a calculator, I'm going to switch it back into its kind of fractional form. So I'm going to make them positive exponents. I'm going to cancel out the c's already, so I'm just going to reduce to those 2 pieces. Positive 2 where? So I'll just kind of talk about all the 2's that we've got floating around. So the first 2 in the exponent came from negative 3 plus 1. So negative 3 plus 1 gives us negative 2. And then I have to divide. Yeah, didn't I make? Oh, I brought it down as a. I see what you mean. Sorry about that. Yeah, I have a positive 2 here, but then magically it turned into a negative 2. Sorry about that. Yeah, no, that should be positive. That was the. I only made it negative in that one spot, but yeah, that was my bad. Sorry about that. So if I change it back to kind of its fraction form to help me do this in my brain, I'll get 2 over 1 minus 2 over 16. So essentially 2 minus 1/8. So if I think about 2 in terms of eighths, I'll get 16 over 8 minus 1 over 8. So 15 over 8 will be my answer. So Wiley here would want 15 over 8 instead of the decimal. Now, of course, your calculator can take a decimal and change it back into a fraction most of the time. So you can kind of get away with using your calculator a little bit, but you will need to know how to do these by hand, so I suggest just doing them by hand. Oh, I did forget to say something also as well, so let me go back really quick. In terms of the homework that's due tonight, so in 6.2, we were doing these, antiderivatives, and sometimes they were phrased in terms of integrals and sometimes they weren't. We were always tacking a plus c at the very end. Now in Wiley, it'll ask you to find a couple of antiderivatives. Now, because they're very specific in their phrasing, they will accept an answer without a plus c. Because they say something like find an antiderivative, and since if you let c be 0, that's technically an antiderivative, that's why they accept it. They'll also accept it if you do tack on a plus C at the end. I suggest, if you haven't done them already, if you've done them, it's fine. But if you haven't done them already, I would suggest tacking on a plus C to all of your antiderivatives just to get used to it. Because in terms of whenever I'm looking at an antiderivative, I expect the plus C to be there. Okay, but Wiley will accept it without a plus C because that is technically an antiderivative. But usually when we're doing antiderivatives, we want this most general, so we want the plus C at the end. Hopefully that made sense. So I suggest just always tacking a plus C on whenever you're taking an antiderivative ever. Okay. Questions on that one? I'll wait 5 seconds before I start the next one. Okay, so here we want the antiderivative of 1 over x. So since that's x to the first, this does turn out to be the natural log case. It's not an anti-power rule because the anti-power rule does not work for when n is -1. So the antiderivative here will be the natural log of the absolute value of x plus c. So remember, I explained why the absolute value was there last time, but remember, it's essentially because if you take the derivative of the natural log of x or the natural log of -x, they both come out to 1 over x. So when we're going backwards, we have to kind of take that into consideration with the absolute value. Plug in your top bound. Subtract what you get when you plug in your bottom bound. So we essentially have natural log of e minus natural log of 1. Natural log of e is 1, natural log of 1 is 0, so this just reduces to 1. Now, in Wiley, say it wasn't an e, say it was a 3. So say, this is side note, it was natural log of 3 minus natural log of 1. Whoa, one screen is lagging a lot. There we go. Natural log of 3 minus natural log of 1. In Wiley, that would reduce to natural log of 3 minus 0, so just the natural log of 3. So you would need to type in natural log of 3 instead of a decimal. Also, when it comes to the absolute value, since the absolute value of 3 is just 3, you can just put it as the regular natural log of 3. But if it turned into the natural log of -3, then you'd have to switch it before you can change to parentheses. But if it's a positive number in there, of course, the absolute value of a positive number is just itself, so you can switch back to parentheses. So that's a note about your Wiley homework, is that be really careful if your answer has natural logs in them, it will actually want the natural logs in the answer, else it'll tell you that you're wrong. Okay, let me erase that so that people don't get confused later, but it will be part of the video in case you forget. All right, this last one then, we have the integral from 0 to 1 of 8e to the 2t dt, so that 8's going to come along for the ride when we try to find the antiderivative. We're in e to the kt situation, so our antiderivative rule for that says to essentially keep the e to the kt, but then we essentially have to divide by that k value or bring it out as a fraction in the front, 1 over that value, plus c. So we'll get 4e to the 2t plus c from 0 to 1. Plug in your top bound. Subtract what you get when you plug in your bottom bound. Wait for the screen to stop lagging. We'll get 4e squared minus 4e to the 0. Anything to the 0th power is just 1. So we'll get 4. 4 times 1 to 4. And this is what Wiley would want. So again, if you were to punch that integral into your calculator, you would get a decimal, and there'd be no way to figure out what that decimal should be in terms of this, so you'll have to do that one by hand, okay? So Wiley wants exact answers, so be very careful about that. Also, remember, if you have, you're trying to type in something like x to the 3/2 in Wiley, always remember to put the power in parentheses, or else it will tell you you're wrong. Even if it's something like x to the 15th, it's usually better about those, but I would always just suggest putting every power in parentheses, really, to just save yourself some trouble. But if you think it's Wiley notation and you think you're right, as always, just email me. Any questions on any of that? Because that is the end of 6.3. So essentially 6.2 is the indefinite integrals, the ones without bounds. And then 6.3 is the definite integrals, the ones with bounds. And now we're done 6.2 and 6.3. So if there are no questions, we'll pop over to, we're going back to chapter 5. I'll hold on a couple more seconds before I jump over there in case people are still writing stuff down. But we'll start 5.3 in just a moment. So Grace, it's going to slightly depend on how much we get done by then. But so far we've covered 5.1, 5.2, 6.2, 6.3, and I'll be sending out, you know, that usual, by the end of the week, you'll have the practice problems, which also tells you what sections it'll cover. But so far we've covered 5.1, 5.2, 6.2, 6.3. We'll cover 5.3. And then I would really love to cover 5.4 because like that's the last thing that I really want to have on the test, but I don't know if we'll get there. So it'll cover 5.1 to 5.3, 6.2, 6.3, definitely, and maybe 5.4, but we'll see. Oh wait, no, I wanted to get through 5.5. Oh well, we'll get where we get. Anyway. So popping over to 5.3, which I forgot to pull up really quick, but it's right here, so here we go. So 5. Why is it not letting me share it correctly? That's just dumb. So I have to share it like this. Just shove that in the corner. Okay, so 5.3 is about the definite integral as area. So I kind of already said this at the very beginning of class to remind us, but remember, so from 5.1 and 5.2, we essentially know that the area underneath of a function, so the area underneath the function f between some two values a and b, that's equal to the definite integral from a to b of f of x. So remember, these two things are related. So say we wanted to calculate these two integrals, and we're going to go ahead and calculate them by hand. So some of 5.3 we'll do in our calculator. If you don't have a calculator that has the capability, then you'll have to do it by hand. But we'll do these two by hand since that's what we were just practicing. So we want to take the integral from 1 to 2 of x squared minus 1. So we need the antiderivative first. So we'll add 1 to the power and divide by the new power. I'm going to bring it out as a fraction to start with because I will run out of space if I don't. Antiderivative of 1 is x, and then plus c, and we need to go from 1 to 2. We'll have 1/3 2 cubed minus 2 plus c minus 1/3 1 cubed minus 1 plus c. Two cubed is 8, so we'll get 8/3 minus 2 minus 1/3 plus 1. If we combine those two fractions together, those gives us 7/3. It gives us. And then -2 plus 1 will be -1, so that'll be a -3/3. So 4/3 is our answer here. And then if I do a very similar thing, but with different bounds now, so it's the same integrand. Remember that integrand is the name for the function that we're integrating, but our bounds are different. So it's the same antiderivative. but now we're going from -1 to 1. So top bound, subtract what we get when we plug in the bottom bound. C's will cancel each other out. We'll get 1/3 minus 1 plus 1/3. So that'll be plus 1, so then minus 1 again. So this will essentially be 2/3 minus 2, and if we treat 2 as over 3, that'll be 6/3. So this will reduce to -4/3. Now, if I just said above that integrals are supposed to tell us the area underneath of a function, how can one of these turn out to be negative if we're talking about area? Usually when we talk about area, we never talk about negative areas. So what the heck is going on here? So let's think about this. Well, not think about it. I'll try to keep those integrals up there. Let's look at what these integrals kind of look like based off of the function. So here's our function x squared minus 1. It's graphed right there for us. So if we think about what these are actually finding, if we look at the first one, that's going from 1 to 2. So that's essentially finding this area in here. And then if we take the second integral that we were finding from -1 to 1, that's finding all of the area in here. It does still find its area, but note what's the only kind of difference between the two areas besides their shapes is that one of them ended up above the x-axis, the other one ended up below the x-axis. And the one that ended up below the x-axis is the one that was negative. So essentially what we have here is when f of x is positive for some x values and negative for others. And I was really bad here and I didn't put a dx at the end of this integral back here. You should always have dx on an integral. So if it's positive for some values and negative for others, let's say that a is less than b just to make this integral make sense. So then the integral is the sum of the areas between a and b, and we're going to have the sum of the areas above the x-axis. Those are going, oh my goodness, those are going to be counted positively. And the areas between a and b below the x-axis counted negatively. So essentially when we're finding these general integrals, even the ones with bounds, maybe I should be careful with the word general. When we're finding these integrals, it's essentially saying any area that ends up below the x-axis is actually going to be counted negatively, and any area that's above the x-axis is going to be counted positively. So it still is finding area, it's just finding us what we usually call a signed area. So there's area below the x-axis, it's negative, so it has a sign of negative, and area above is positive, so it has a sign of positive. So it's usually called a signed area. And for the most part, there's a bunch of questions that we can ask where we don't care, you know, what's above and what's below. We just want to calculate the actual integral. There's plenty of those where you don't need to worry about what's above, what's below, what's here, what's there. But in other cases, we actually do want to consider it. So before we get to that, and we might not get to too many of those examples today, but say we want to find the integral of x cubed from -1 to 1. So let's do this one more by hand, because it's not too bad. So if we find the antiderivative, we'll add 1 to the power and divide by the new power. So I'm going to bring that divide by the new power out front just to save myself a little bit of space. Plus c from -1 to 1. So if we plug in our top bound and subtract what we get when we plug in the bottom bound, the c's are going to end up canceling each other out. We're essentially going to get 1/4 minus 1/4, so 0. Now again, we're talking about an area here. How can an area be 0? Well, if I think about what this function looks like, x cubed, this. So essentially this area that I'm finding here from -1 to 1 is essentially this area here. So it essentially turns out that the area below the x-axis turns out to be the same amount of area above the x-axis, and they end up canceling each other out. So that's why the integral being 0 does make sense. Now, again, in general, there's some situations where that would be our answer. It would be 0. That's what we would want. But there are other situations where we actually kind of want to know, well, how much stuff was there actually? Like, I know that there was some stuff there. Obviously, there's stuff that I've shaded there. So how much of that is there? And sometimes we're going to want to know that. And that's essentially what 5.3 is all about, is being able to find that actual amount of stuff, if you will. So again, I don't know if we'll get to an official example, but what we're going to do now is we're going to write down the process for these types of questions. Now, there's this type of question where I can say, well, what's like it's going to be called total area questions. So I can ask you, what's the total area bounded by x cubed and the y-axis? And that would be asking you to find all of that orange stuff that I just shaded. But then we're also going to look at area between two functions. So I'm going to have two functions. There's going to be some area bounded by both of them, and I want to find the area between them. And in general, they can be thought of two separate processes, but I'm going to present them as one because you can use one process to do both types of questions. If you've seen calculus before and you've done total area questions, you would have done them with absolute values. If you know how to do that, go right ahead. I'm going to present total area questions as the same as an area between two functions because technically it is. So just in case you know calculus and you possibly know what I'm talking about. Otherwise, don't worry about it. But anyway, here's the process that we're going to be following. The first thing you're going to do is you're going to find where the two functions intersect. And you might say, okay, well, if we're looking at the one you were just talking about of x cubed, what's my second function? Well, again, when we want to do something like that, it'll be called a total area question. And for those, your second equation is just y equals 0, the x-axis. But in general, you might be given two functions and you're going to set them equal to each other to find out where they intersect. Now, because of the next thing I'm going to want to write, say that you find that they intersect at some c value, some x equals c. Sorry, does someone have their hand up? Sorry, what's it? Aiden? Oh, maybe you're typing something. Aiden, you have your hand up.
Yes, I do. I'm sorry. I forgot about that. I had a question on the last example, just a quick one.
Yeah.
So we wouldn't carry over the plus c. It would just be 0, not c.
So I haven't been writing it out. Maybe I should have. Essentially what happens is we get 1/4 plus c minus 1/4 minus c, and the c's always end up canceling each other out. So when we're doing these ones with the bounds, the c's always end up canceling, so they're never part of our answer. I probably should have written that out officially at least once, but that's essentially what happens is they cancel you out.
That's fine, thank you.
Mm-hmm. Okay, so where was I? So we're going to set these two functions equal to each other. Let's say that the number you get when you set them equal to each other is c. Okay, what you're then going to have to do is split up the integral based off of any values that you find. So say we're going over an interval from a to b. Say this was our given interval. Well, essentially you'd be looking for the integral from a to b, but what we're going to do is we're going to have to split it up using that value where the two functions intersect, if there is one. If there isn't one, then you skip this step. But you essentially have to split it up into 2 or maybe more integrals. The reason we have to do that is because essentially we need to make sure that any area that's, say, below the x-axis actually gets counted as positive. Because remember, at this point, what we're actually trying to do is we're trying to find the total amount of stuff. So I don't care if it's below the x-axis, I want to figure out how much stuff is there. So essentially we have to split it up. Now, if you're not given an interval, and again, we're writing out the full process right now, so a lot of this is like, whoa, what do you mean? We'll do a few examples. We might not get to it until Wednesday, but we'll be doing some examples in a couple minutes. If you're not given an interval, then you're going to use the values that you find to essentially make an interval. So sometimes you're given an interval to work over, sometimes you're not. And if you're not given an interval, you just make it out of the values that you get when you set the two functions equal to each other. But you're going to calculate the integral from a to b, and this line is not quite long enough for what I want to write here. I'm going to write top minus bottom, and I'll explain what I mean by that in a second. And so you're going to do that for essentially each integral. So essentially what happens here, even when we're finding total area questions, but say I phrase this more in terms of an area between two functions. So say I have some f of x and some g of x, and I want to go between 0 and let's just call it b. We'll call b right here. Let me write it like this, 0 to b. So essentially what we want is we want the area in here, but then we also want the area in here. This is also true for if it's between a function and the x-axis. So even the one we were just looking at with the x cubed, you know, we would be looking at the x-axis compared to where the function is. So notice in like the left part, the x-axis is above the function, and in the right part, the function is above the x-axis. But anyway, hopefully this will make a lot more sense when we do official examples. So we want all of that area, but notice that in the green section, essentially in the green section, let me color these. So f of x is going to be blue, that's blue. So for the green area, f of x is above g of x. Let me make g of x pink. But then essentially for that red area, it kind of switches. And that's going to make a huge difference about kind of which function is above the other. So that's what I mean by a top versus bottom. Which function is on top of the other in that interval? Now there's two ways to find which one is on top of the other. You can either graph the two functions and just look at it and say which one is above the other. So say this was one we were actually trying to calculate. We can look at this and say, okay, well, in that first piece, the f of x is above g of x, and in the second piece, g of x is above f of x. Or you can do it algebraically, and we'll see that we might get to one example in a minute, where you're essentially going to choose an x value in that section, plug it into both functions, and see which y value is larger. The larger y value goes to the top function, the lower y value goes to the bottom function. So that's a big process for kind of two different types of functions, two different types of problems we're going to be looking at. I'm going to skip writing it down formally for now. We'll write it down formally on Wednesday because I want to get to this first example. So you can hopefully see all of that stuff we just wrote down. So say I essentially want to go back to that idea of that question we asked before we wrote down this process. What is actually the amount of stuff that's between x cubed and the x-axis on -1 to 1? So this is kind of how they would usually be phrased. There's a couple other ways, but this is the main way. They'll ask for the total area for a function, and that essentially means the area between x cubed and the x-axis, which remember is just y equals 0. So if we use the process we just wrote down, we essentially have to find the area between these two functions, x cubed and the y-axis. So we're going to set the two equal to each other. So we're going to find where they intersect. Let me kind of try to write down the process as we go. So we set these two functions equal to each other. that will just give x equals 0. Then we need to figure out if we're going to split the interval, which will also split the integrals. This is where I start confusing my words interval and integral, so I need to be really careful. So essentially, we're going over, -1 to 1, because we're told to do that. Now, x equals 0 is in that interval. So since 0 is in that interval, essentially we're going to be working over -1 to 0 of something that we'll figure out in a second. And then from 0 to 1 of something. So we're going over that entire interval from -1 to 1, but since they intersect at 0, we're going to have to split it up. Now we have to figure out top versus bottom. I'm going to do this algebraically, and then I'll talk about the graph way in a second. So we're essentially now on two intervals, -1 to 0 and 0 to 1. And you kind of think of these as kind of separate pieces. You're going to pick a number that is in that interval, any number you want as long as it's in that interval. You're going to plug it into both functions. So we have x cubed. That will give us y equals -1.25, I believe. Yeah. -0.125. And if I plug it into y equals 0, well, that just gets me y equals 0. Let me try to clean this up the tiniest bit. Nope, decimal's in the wrong spot. There we go. Which one of those two numbers is larger? 0 is. Barely, but it's larger. So that means that this one's our top function. And hopefully you'll see what I mean by top function in a second. And then here, if we plug in positive 0.5, if we plug it into x cubed, we'll get positive 0.125. And if I plug it into y equals 0, I'm just going to get 0. Which one's the larger number in that case? Positive 1.25. If we were doing this with a graph, essentially this is where, well, in this first piece, from -1 to 1, the x-axis is above the function, so the x-axis is on top, and in the second piece, the function is above the y-axis. The 0.5, so essentially I'm working over two intervals now. I'm going from -1 to 0 and 0 to 1, so I just chose a number between 0 and 1. So I chose 0.5. You can choose absolutely any number you want. It's kind of like when we were doing those number lines with the derivatives and you can choose whatever point you wanted. Same kind of idea here. You're breaking it up into these intervals and you can choose any point you want in that interval. And you're going to take that point that you choose and plug it into both functions. I'm running out of time, so I'm going to write down the answer and we'll talk about it a little bit more on Wednesday. But essentially at this point, what you have now is you have your two integrals. And so we have in the first interval, 0 was the top function. So we have our top function minus our bottom function. And we always need dx. And then in the second piece, the top function was x cubed, so top minus bottom. And I know when it's 0, you don't really have to write -0, but I'm trying to be very specific here. At that point, for these types of questions, you could plug those into your calculator if you wanted to. You don't have to do them by hand for these types of questions. Again, you still need to know how to do them by hand. But for these types of questions, they're long enough and tedious enough that at this point, if you wanted to, you could plug it into your calculator. If you're curious, the final answer is going to come out to be 1/2. Again, I'm going to talk about it a bit more on Wednesday, but I'm out of time now. So we'll kind of review that one on Wednesday and do a couple more. Got a ton more. But essentially, this is how they work, is we're going to essentially have to split it up wherever it crosses the x-axis. And then we're going to have to figure out these intervals, top minus bottom, in each case. Your quiz on Wednesday, for those of you who might have to leave soon, is, well, or just want to leave. 6.2 to 6.3. So antiderivatives and finding definite and indefinite integrals. So essentially kind of what we were doing on the packet right before we jumped to 5.3. That whole packet is kind of what's fair game on your quiz on Wednesday. So we're out of time, as I already said. If you need to leave, feel free to leave. If you have any questions,